Alright, so for today we are going to revision on the chapter 6 and 7. So do check out the next few couple of minutes on chapter 6 and 7, and there will be strategies given on how to answer questions in regards to covalent molecules.
Alright, so we're going to get started. We will look at chapter 6 and 7 quiz for now. So question number 1, it says select the best definition of a molecule from the alternative below. So if you look at A, it says a group of two or more atoms bonded due to transfer of electrons between them. B, the smallest possible part of a compound that can exist on its own. C, a group of two or more atoms linked together by sharing electrons in a chemical bond. Or is it D, a compound formed when atoms share electrons? So today we are looking at covalent structure, covalent or simple covalent structure. So they are asking you which of these options is correct. So most likely your answer will be C, a group of two or more atoms linked together by sharing electrons. When we are talking about covalent structures or covalent molecules, we are talking about sharing of electrons. Sharing of electrons. And it's a simple covalent structure. So it must be, in this case, two or more atoms that are linked together by sharing electrons in the chemical bond. So that is the answer that we have for question number 1. It has nothing to do with transfer of electrons. When we are talking about transferring electrons from one element to another, that will be related to metal compounds. So in this case, if we are talking about covalent structures, we are talking about sharing of electrons. Question number 2. The electron configuration of sulfur is 286. When it forms a compound with hydrogen, the chemical formula is likely to be. So when we are talking about sulfur, sulfur is in group 16, which means that they have 6 valence electrons. If we are talking about sharing electrons, they want to fulfill the octet rule. Fulfill the octet rule. So the only way, in this case, for sulfur to fulfill the octet rule is to have 2 more valence electrons. So when it forms a compound with hydrogen, we will know that in this case, sulfur will need 2 more valence electrons for it to become stable, and each hydrogen has 1 valence electron because hydrogen is in group 1. So what you need to do here is that when you have a combination of sulfur and hydrogen, you will know that your answer here has to be B, because you have 2 hydrogen for every single sulfur that is present. So sulfur will share 2 valence electrons and hydrogen will share 1 valence electron each. So your answer here has to be H2S. Let's look at question number 3. In the fluorine molecule, they are. So when we are talking about fluorine, and we know that these are what we call the lone pair electron. Why is it lone pair? Because you do not have any bonds between the valence electrons. So in this case, no valence electron has been shared for the lone pair electrons. So these are lone pair electrons that has not been shared. And we know each fluorine atom contains 7 valence electrons. So there is a bond in the middle that shows the sharing of valence electron between these fluorine atoms. And this is also, in this case, is also known as the valence structure. If you still remember, there's a difference between electron dot and valence structure. So in this case, a valence structure because it shows the bond using that line. So which of these is the answer? Most likely your answer will be D. 6 non-bonding electron pairs, 1, 2, 3, 4, 5, 6. 6 non-bonding electron pairs, so lone pair electrons. And they have 1 bonding electron pair, which is the one in the middle. You can see that. Alright, so question number 3, the answer is D. Question number 4. Question number 4 is showing you the structure of ammonia. How does ammonia look like if you're trying to create a model? So I've created a model here, as you can see. This is a model of ammonia. You can see the blue is the nitrogen, and the one that is in white, these are the hydrogen atoms. You can see that. So this particular structure is NH3. If we are going to draw the electron dot diagram, and we know nitrogen has 5 valence electrons, so it's 1, 2, 3, 4, 5, and it's sharing one electron or one electrons with each hydrogen atom. So this is actually a ball and stick model. You can see through this particular diagram, this is a ball and stick model. So you have ball and you have sticks. So your best answer here has to be A. Some of you may be like, how about tetrahedral? Is this a tetrahedral shape? The answer is no, because if we are talking about methane structure, let's say CH4, if you have one atom be bonded to 4 other atoms, then it will be tetrahedral. In this case, can you see that you only have one atom be bonded to 3 other atoms? One atom be bonded to 3 other atoms. And the one at the top here is what we call lone pair electrons. So this one here is the lone pair electrons. So the repulsion, if you're talking repulsion of that lone pair electron, will be different from the bonds that you see here. And that's the reason why this particular structure is trigonal pyramidal or trigonal pyramid and not tetrahedral. So if there's a difference in electronegative value, so if we look at this diagram here, there's a difference in terms of electronegative value because we know different elements have different electronegativity. And because there's a difference in the electronegativity between nitrogen and hydrogen, it creates the dipole moment, and at the same time is polar. Question number 6. It says select the alternative that correctly lists the properties of molecular compounds. Is it A, low melting point ductile and conducting electricity as a liquid? Is it B, low melting point, lattice structure and brittle? Is it C, high melting point, non-conductive of electricity and hard? Is it D, low melting point, non-conductive of electricity as a solid and as a liquid? So most likely your answer here is D, because if we are talking about molecular compounds, we are talking about simple covalent structure. Simple covalent structure. So if you are talking about simple covalent structure here, they have to have low melting point, non-conductivity of electricity as a solid or liquid. If you're talking about a particular compound that can conduct electricity, let's say in both solid and liquid, then it is a matter. If it can only conduct electricity in the aqueous or molten state, then it will be an ionic compound. So in this case, if they cannot conduct electricity in both solid and liquid, then it has to be a simple covalent molecule, such as water molecule and carbon dioxide gas. Question number 7. Oxygen gas can be cooled to a liquid and then to a solid sample of oxygen contains. So which of these do you think is the correct answer in regards to a solid sample of oxygen? The best answer here has to be A. If we are talking about oxygen, there is a covalent bond between the oxygen atom of that particular molecule. But if that particular structure here is solid, the molecules are held together in a set arrangement. That's the reason why it can't move around if it's a solid state. Question number 8. A triple covalent bond can exist between, is it A, 2 atoms that have 3 electrons in the outer shell, B, 2 atoms that have 5 electrons in the outer shell, C, 3 different atoms that require an electron each to complete their outer shell, or is it D, an atom with 5 electrons in the outer shell and an atom with 7 electrons in its outer shell? If you're talking about a structure that has a triple covalent bond, a very good example will be a group 15 element. If you're talking about a group 15 element, we know that they have 5 valence electrons. For example, if you're talking about nitrogen, they have 5 valence electrons. 1, 2, 3, 4, 5. And what nitrogen does here is that it forms a molecule with another nitrogen atom, and now they have 8 valence electrons, or each nitrogen will have 8 valence electrons in the outermost shell. So your best answer for this question has to be B. Why? Because if you have 5 valence electrons or 5 electrons in the outermost shell, you can see that they are sharing 3 valence electrons with another nitrogen atom. That is the reason why it forms the triple covalent bond, so that it can fulfill the outer rule and will become stable as a result. Alright, so if we look at the short answer questions, question number 1 is looking at phosphorus trichloride, PCl3, in a covalent molecule made up of phosphorus atom and chlorine atom. It says PCl3 is toxic, highly corrosive, and reacts violently with water. Describe the nature of the covalent bonds that form between P and Cl atoms in a molecule of PCl3. In your answer, you should state whether the PCl bond is polar or non-polar. Explain what makes the bond polar or non-polar. If we are talking about phosphorus and chlorine, we know there's a difference in electronegative value. What is electronegative? It's basically something to do with the tendency of the atom attracting electron. The higher the number that you find in the electronegativity, the higher the tendency of that particular atom attracting electrons. So if we are talking about phosphorus here, we know phosphorus has an electronegative value of 2.19. Chlorine has an electronegative value of 3.16. So the question here, once again, is it polar or non-polar? If the electronegative value is the same, then there is a chance for it to be non-polar because the net dipole will be 0. Or there is no net dipole. But if the electronegative value is different between the atoms, then there is a chance that that particular bond, or in this case the bond, will be polar. So in this case, we can say that PCl bond is polar because there's a difference in electronegativity between the phosphorus and chlorine atoms. And we can say that chlorine is more electronegative than phosphorus. So in each of the PCl bonds, the electron density will be found closer to the chlorine atom, which is correct. Because chlorine here, if you look at the bond once again, PCl, we will see that this will become partially negative, it will become partially positive. Bear in mind, we are not talking about charge here. There is no change in terms of the charge of phosphorus and chlorine, but chlorine will become slightly negative because the electrons, or there's a higher tendency for electrons to be attracted to chlorine. So we can say that the resulting dipole, or the resulting bond dipole, will point from phosphorus to chlorine. Alright, so that is a general idea of how bond dipole works. So let's look at question number 2. The electron dot diagram for bromine looks like this. So they're asking you for the valence structure. What is the valence structure for a bromine molecule or bromine molecule? If we are talking about bromine or bromine here, how do we draw the valence structure? Bear in mind, the electron dot and the valence structure are two different things. So in this case, when we are talking about valence structure, what you need to do, you need to have 7 valence electrons for each of these bromine or bromine. We know that they are sharing 1 valence electron. So you have 1 bromine, you have second bromine, and then they have 7 valence electrons. So because they share 1 valence electron with another, or with one another, at the end of the day, they will be able to fulfill the octet rule by having 8 valence electrons in the outermost shell. Question number 3, the atomic number. Atomic number means the number of electrons. So the number of electrons of chlorine will be 17. And the atomic number, which is number of electrons for hydrogen, will be 1. What is the Lewis structure? Bear in mind, Lewis structure is different from valence structure. The Lewis structure is basically the electron dot diagram. Electron dot is also known as the Lewis structure. So how do we draw the Lewis structure? So you have 1 hydrogen, you have a chlorine, so they share 1 valence electron with one another. So you usually represent by dot and crosses, as you can see here. And that is the general idea of how you draw the Lewis or the electron dot of hydrogen chloride. Electrostatic attraction between the hydrogen atom and the lone pair of electron. Between hydrogen atoms and the lone pair on the oxygen atoms of the neighboring water molecules. So when we are talking about hydrogen bonds, once again, we are talking about the bond between one molecule and another molecule. So the bond between one molecule and another molecule. So in this case, because of the presence of the lone pair electrons on each of these water molecules, and we know there's a covalent bond between hydrogen and oxygen, it will enable the formation of electrostatic attraction between the hydrogen atoms of one water molecule and the lone pair of electrons of another water molecules. So that is in general how it works. And what we know from water molecules is that they can form a maximum number of 4 hydrogen bonds. Each water molecule can form a maximum of 4 hydrogen bonds. So the general idea is that when a water molecule is present as a solid ice, it's able to form 4 hydrogen bonds with 4 different water molecules, enabling, and this occurs in solid or solid ice, and enabling them to contain an open space, ultimately allowing it to form the ice structure that has a low density. Solid ice structure that have a low density. Do you still remember what is the formula of density? Density equals to mass divided by volume. So in general, if you have a greater volume, so if you get an opposite, you get a greater volume, your density will decrease. So that is generally the idea. If you're talking about, let's just say, when the ice melts, what happens when the ice melts? You will get a reduction in open space. Why? Because the hydrogen bonds are now broken. Hydrogen bonds, or some of the hydrogen bonds, starts to break, which then result in reduction in their open space, which means that the density now will actually increase as a result. Which is why if you have a cup of ice cold lemon tea and you put ice cubes into your lemon tea, for example, you can see the ice cubes actually floats in that particular beverage that you have, or in the cup that you have. Why? Because the ice has a lower density, and due to it is capable of forming 4 hydrogen bonds with 4 other water molecules, it will have a lower density, it will float on top of the liquid water. Alright, let's go through the last question of today's session. So last session here, there's 2 different components. So the first one here is showing the structure of boron trifluoride. So we have 1 boron and 3 fluorine atoms. So what do you think is the answer to this? Is it polar or is it non-polar? How do we know? If you look at this structure here, can we say that this structure is symmetrical? Most likely yes. How? If I show you an atom and I've created this particular compound or structure, can you see that this is actually boron trifluoride? So I try and spin this. This is boron trifluoride. You have 1 boron atom in the middle and 3 fluorine atoms. And you can see that this structure is actually symmetrical. So there's no lone pair electrons on boron, and it looks symmetrical. And this particular structure has the shape of trigonal panel. So it's symmetrical. In this case, this particular compound has the shape of trigonal panel. And this structure here is actually non-polar. It's non-polar because it's symmetrical. When you get a structure that's symmetrical, most likely it is non-polar. So we can see the bond dipoles will cancel each other out, leading to a no net molecular dipole. So there is no net molecular dipole. If you come across a structure that has no net molecular dipole, then it has to be non-polar. Alright, so continue with that particular question on question number 5, and this is the second part of it. We look at boron trifluoride. We know boron trifluoride is non-polar. And once again, this is the structure of boron trifluoride. Alright, boron trifluoride. But let's just say now we are looking at, you have phosphorus trifluoride. Phosphorus trifluoride, if I'm going to build a ball and stick model, so this is a ball and stick model. Once again, you have ball and you have stick. So if you look at this particular structure here, can you see this is slightly different from the previous structure? Let me show you. If I show you the previous structure, this is more flat. So boron trifluoride is more flat, as you can see. If you compare to this particular structure, you can see that at the top there's actually a lone pair electrons, which is at the top. Can you see here? Lone pair electrons, which is at the top. So which means that because it has that lone pair electrons, you can see that this particular bond is more bent towards the bottom as compared to the previous one that is more flat. So in this particular case here, we can see that this particular structure is asymmetrical. Why is it asymmetrical? It's asymmetrical because when we are talking about the structure here, the net dipole cannot cancel each other out because of the presence of the lone pair electrons. When you come across to have lone pair electron, it's asymmetrical because you cannot break up on the left, on the right, it can't really reflect one another. And as a result, this particular structure here has to be asymmetrical. And because it's asymmetrical, this is now a polar molecule. It's a polar molecule. It contains that one lone pair electrons. And because the net dipole moment cannot cancel one another out. When I talk about net dipole, once again, there is a difference in electronegative value here. And the thing is that they cannot cancel each other out because of the presence of that lone pair electrons. And as a result, this is a polar molecule.